All right. So I'm going to pick up where I left off last time because we were kind of in the middle of an important question. But just to get everybody back up to speed. So the general topic was whether or not we could figure out what sets limits to the precision of cell sensing, in particular how precisely a cell could sense a uniform concentration. And I would say the sort of running theme of last time was that if you were to ask what is the relative error that a cell makes in its estimate, and we quantified that by the standard deviation in some estimator of the background concentration divided by the mean of that estimator, then up to a prefactor that was dependent on the model, we got results that look like 1 over the square root of the size of the cell, the diffusion coefficient of the molecules, the mean concentration of the molecules, and how long the cell waits. But we ended on an important question, and that was that none of the models that we considered were very realistic for one important reason. They all assumed that every molecule that arrived at the cell surface was counted by the cell in some way, either by monitoring or by absorbing or whatever. And so once again, following the work of Howard Berg and Edward Purcell, we then asked, how does this change if we explicitly account for a finite number of small receptors on the surface of the cell? And in particular, I'm interested in the question of if the cell can only absorb molecules through little receptors or little patches on the surface, then how much does that cut down the amount of molecules that it actually absorbs? So we had this model where the cell is still a sphere, but it has these patches on the surface, and a molecule can come in and hit the surface, and maybe it'll get unlucky and it won't hit a patch. And so maybe it'll start diffusing away, and then maybe it can try again, and maybe it'll try again and again, and maybe it'll get unlucky for real, and it'll ultimately diffuse off into infinity. And we gave these events certain probabilities. I believe that I called the probability of arriving at the cell surface from some location close by 1 minus p, and the probability of hitting the cell surface but not hitting a receptor, q, and the cell was size A, the receptors we called size S, and what else? And we reasoned that in order for it to bounce off and then come back and have sort of or in order for us to characterize the return as something independent from the point at which it left, then it has to go away a certain distance, and that distance would be on the length scale of the receptor size. So I'll call this distance that it goes away A plus S, right? And okay, so we counted up all the possible ways that this can happen, and it was a geometric series, and that allowed us to calculate the probability that the cell escapes forever. What we really want is the probability that it's absorbed by the cell, which is 1 minus the probability that it escapes forever. And the result of the geometric series was, I believe, p over 1 minus quantity 1 minus p times q. Yeah, sorry, I have it backwards from my notes as I mentioned last time, so I hope this is okay. Or at least it's consistent with what I wrote last time. Okay, and at the very end we calculated q, right? Q is just obtainable as a ratio of areas, right? So if there are, so the total surface area of the cell is 4 pi a squared. If there are capital R receptors, and each one has an area, say, of pi s squared, then this is the total area of non-receptor surface. That divided by the area, the surface area of the cell, is the fraction of area that's non-receptor surface. Okay. So this specifies everything except p, or 1 minus p, right? So how do we find 1 minus p? Specifically, what's the probability that if a molecule is sitting at a distance a plus s, and for convenience I'll just call this b, if a molecule is sitting a distance b away from the center of a sphere, what's the probability that it actually hits the surface of the sphere instead of never hitting it and diffusing away to infinity? So there are several ways to get the answer to this question. I'll present the way that is presented by Howard Berg, and that way uses a flux argument and the diffusion equation. And so the rationale is the following. So you can imagine this molecule, I mean, it starts at a distance b, but the argument's going to be completely independent of what angle it starts at, right? So we can equivalently imagine smearing that molecule over all angles, but always at a radius b. So imagine slightly morphing the problem into a molecule that's smeared into a spherical shell, but it's still a distance b away. Okay, and instead of thinking that of that as a molecule, I want to now think of it as a source of continuous molecules, for example. It doesn't really matter how strong that source is, because all we're going to care about is the ratio of flux from that source in to an absorbing boundary at A, the ratio of that to the flux either in or out, where if it goes out, it can be absorbed by another boundary whose distance I'll call d. Okay, not c, because that variable is reserved. And as you might imagine, we're going to take d to infinity, right? We're going to get an answer. We're going to take d to infinity. So being absorbed by A is hitting the cell. Being absorbed by d is diffusing away to infinity, and we want to take the ratio of A to both possibilities. That'll give us our probability 1 minus p. Okay, so just to put that so that we don't forget, the claim is that 1 minus p is the ratio of flux into the surface A, which is absorbing, over flux into the surface A plus flux into the surface D, which is also absorbing. Okay, so this is a steady state problem. We've turned the molecule into a continuous source. And so if we think first about what the concentration of, stuff from that source is going to look like as a function of radius, then I hope you'll agree that because there are absorbing boundaries at A and D, the concentration will be 0 there in steady state. Okay. And then at B is where the source is. So at B, that concentration is going to be maximal. Okay. I don't really care what this maximal value is, because all we're going to care about is the ratio, and that value is going to cancel in the ratio. But for now, I can call it C max. And if that's the maximal value, then this has to somehow go from there to 0 on either side. Okay. And so what we have is essentially two regimes in which we need to solve the steady state diffusion equation, and that will give us the flux via a derivative, and that will give us this 1 minus p, and we'll be done. Sound good? Okay. First regime, R between A and B. Now, in either regime, of course, we have the diffusion equation, C dot equals d del squared C, and we just care about steady state in this context, and so it's very easy. It's spherically symmetric as before. And we have C of r has to be some constant b minus some constant a over r, right? This is the only formula that will solve, or expression that will solve the spherically symmetric problem. Okay, and we have two boundary conditions. It has to be C max at B, it has to be 0 at A. And enforcing those boundary conditions leads to the expression A times B times C max over A minus B. No, over B minus A, let's keep it positive. Times 1 over A minus 1 over R. Okay, and you can just check that that's right? If R is A, we have 0. If R is B, then we have B minus A over AB, and the AB's cancel, and we get C max. Good. And then, analogously, for R between B and D, we have a similar thing, except the B is replaced by D, and I probably need a sign flip. No, the A is replaced by D, and I probably need a sign flip. BD C max over, yes, D minus B, and now this is 1 over R minus 1 over D. Okay, yeah? Okay, so now, this is not exactly what we want. What we want is the derivative, because the derivative gives the flux. So the flux into the surface at A is, I want the total flux. I mean, it doesn't matter because it's a ratio. So it's 4 pi A squared is the area of the cell times D times the derivative of C with respect to R evaluated at A. We take the derivative. This becomes a 1 over R squared. We evaluate at A. That kills one of the A's. And we just get 4 pi A squared D times BC max over A B minus A. And then similarly, the flux at D, it's negative because, you know, we want the outward flux into the surface at D. dC dr evaluated at D, and we get a similar thing but with D's, right? It's all over this chalkboard. Okay. So we plug this in to here, and after, are there mumbles? I like mumbles if something's wrong.
In the first part of J of D, it should be T squared instead of A squared.
Oh yeah, definitely. Thank you. Okay. Okay, good. So we take the ratio, most things cancel, and we get that this 1 minus p is some expression, and in particular, if we take, if we take the limit as d goes to infinity, we find that this is a over b. Surprisingly simple. Yes? Yeah, that's right. There is a source, in a way. It's like a single molecule, which is weird. I mean, it's weird to then make the analogy to this problem. But I would argue that you can imagine the problem I'm solving right now as a spherical shell source of many molecules, all happening one after another. And if I take the ratio of fluxes, then that ratio of fluxes is the same as the probability of any one of those molecules of doing the event we care about, which is hitting the surface before going away. Does that make sense? It's kind of like, if you solve the diffusion equation, you can think of it as how a concentration evolves, but you can also think of it as how the probability distribution for any member of that concentration would also evolve, right? Is this a reasonable expression? It looks too simple to me. Does it have okay limits? Are we okay with this expression? I think it's okay, maybe. If B is A, you're already at the surface, so the probability better be 1. If B is infinity, you'll never get there. Yeah, so it's probably the simplest thing we could have guessed, I think. All right, I think we have all the ingredients. We have P, we have Q. B is something I made up, so this is really A over A plus S. So we have P and Q both in terms of A and S, and R, the number of receptors. I can plug that into here. Once again, it's just algebra, and what I get is the absorption probability is RS over 4A plus RS. Also nicely simple, yeah. Yeah, so the whole premise of this argument that led to the geometric series is that I'm counting the ways that a molecule can hit the surface, not on a receptor, so therefore bounce away, come back and hit it again, et cetera, et cetera. But let's say it bounced away and then came back immediately. So the question I would have for you is, should I call that the same bounce or a new bounce? And the only way to answer that question is to compare the distance of the next hit to some relevant distance in the problem. There are two relevant distances in the problem. One is the size of the cell, one is the size of the receptors. But when the molecule is at the surface and you're determining whether or not it's hitting a receptor or not, because the receptors are so much smaller than the cell, the surface essentially looks flat to that molecule. So really, the only length scale of relevance to this bouncing process is the length scale of the receptor. So I have to choose a typical distance it must go away before I call it a new event, and that's the receptor length scale.
Right.
What's that?
You just need to choose something, and since this is the scale in your problem, then you choose.
Yeah, maybe what I'm missing here is the physicist's best friend, right? So this, I will say, I mean, like, it's amazing. Like, every question, I think, this is my ironclad armor. Every question that's been asked so far, the answer has been in this one paper that I'm working off of. So this is not the only way that Berger and Purcell calculated this probability A over B. They did it more exactly, well, more specifically, it's not the only way they calculated this probability. They did it more exactly as well, and there was like a pi instead of a 4. So, I mean, it's just easier to go through the loose argument, as usual. But if you're worried, I'm telling you, you don't have to be as worried.
I'm not worried. I'm just wondering how it will change if you take that distance, after you use or anything else.
If I take the distance of half,
Like that you consider as K, like the surface is B.
if I take B to be larger than this or something, or?
Or something.
Yeah, I mean, the most straightforward answer is it might change some factors here, factors of 2, for example. 4 becomes a pi or it becomes an 8 or something like that. But anything on the order of S gets the physics right, I would argue. Something on the order of A does not, because that's not required for the cell. The molecule doesn't have to go like a whole diameter away to just see if it hits a receptor or not the next time. Okay, is this a reasonable expression? Does it have the right limits? I mean, this is like what you do as a physicist, right? You get something and you say, does it have the right limits? I mean, I think so, right? So what's one limit we want to know? We want to be sure about? Yeah, if S goes to 0, it goes to 0. That's good. If R goes to 0, it goes to 0. If R goes to infinity, that we should recover the fully absorbing cell case. It does, right? Probability of absorption is 1. So I think there's nothing wrong with this expression. Why is it useful? Well, it's useful because, of course, R needs to go to infinity to get perfect absorption. That's what we considered last time. Yeah?
Take that limit as a cell gets larger. It's like somehow I guess, so the cell gets larger and the size of the receptor gets smaller. Like it stays the same charge. Then the probability, I guess the probability still reasonably becomes lower because I guess you're occupying this area for all.
That is how to answer a question without speaking. You just wait. Okay, R would need to be infinity to get perfect absorption, but a very reasonable question is how big would R need to be to get close to perfect absorption? I think that will answer the question of whether, our perfectly absorbing model is reasonable enough. So, for example, what would R need to be to capture half the molecules instead of all the molecules? And the answer, of course, is that R would need to be, RS would need to equal 4A, so R would need to equal 4A over S. Now, the typical size of a cell, especially the cells that Berg and Purcell were thinking about, namely E. coli bacteria, is about a micron. Typical length scale is about a micron, right? So if A is about a micron, the typical size of a receptor is not a micron. It's a lot smaller than a micron, right? Receptors are proteins. They're molecules themselves, so they're bigger than an atom, but they're not as big as the whole cell, right? So something on the order of a nanometer is reasonable, maybe a few nanometers. And if I put in that order of magnitude, then this is 4,000. Right? And one of the questions last time was like, okay, how many receptors do cells really have? And it certainly depends on the cell, but something on the order of 4,000 is very reasonable. It's maybe even low for many receptor types. So that's encouraging, right? It says that, something reasonable, biologically reasonable, is required in order to capture half the molecules. I think that the more impressive thing is that you can actually ask, well, how much of the area is covered up by these 4,000 receptors, right? So the fraction of area covered, area of receptors divided by area of the cell, is R times pi s squared over 4 pi a squared, which is 4,000 times 1 nanometer squared over 4 times 1 micron squared. And now we have 1,000 on the bottom. So this is 0.001 or 0.1%. So that means if your entire surface is covered by receptors, you get 100% of the molecules that arrive. If only 1,000th of your surface is covered by receptors, you get half the molecules that arrive. And that's striking. That means two things. One, it means our model of a perfectly absorbing cell is okay. in my opinion, because that assumes you get all the molecules, and here you get half. Not a big deal. It also means that there's plenty of room for other receptors of other types, right? So a cell can multitask and detect lots of different type of molecules with lots of different types of receptors with affinities for those molecules all at the same time. And that was the main point emphasized, I guess, by Berg and Purcell. Why is this, by the way? I mean, what's the intuitive reason why you can only use 1,000th of your surface to do half the job?
It bounces around.
Yeah, it's all the bouncing. Exactly. That's kind of the intrinsic nature of diffusion. It will bounce around a lot. They did calculate this too. It was something like 50 times on average before moving away. And so there's a lot of chances once it gets in the vicinity to actually be captured. And it's funny because we didn't really, I mean, this sort of goes to your skepticism, we didn't really capture the spatial aspect of the bouncing around or anything. I mean, we did it mathematically with the geometric series, but the nature of diffusion and the importance of diffusion, it's only here, right? It is in the calculation, but it's here. Okay, so for our purposes, what that does, is it makes me feel okay about this, okay? I don't know if it makes you feel any better, but it makes me feel better that the very sort of spherical cow models that we use to get this aren't going to be so bad. Now I'd like to address a question that I would hope is sort of the elephant in the room question, and it's something that Berg and Purcell left to the end of their paper, and that is, does any of this actually matter for what we observe, right? So can we compare this type of thing to experiments, and does this, I mean, this is a physical bound, cells can't do better, but do they really even do this good, or are there many other factors that make this irrelevant? So what do the experiments show? And they asked this for a number of different cell types, but I think the most appropriate one to discuss is the cells that Howard Berg was actually looking at the time. And so he sort of used his own experiments to make this comparison. And that was, of course, E. coli. And so maybe you know this, or maybe someone's talked about this, but very briefly, I need to tell you, the textbook version of how E. coli move. And that is they execute essentially a random walk. They do this run and tumble type motion. They have flagella that propel them forward, and every now and then they rotate the flagella in the opposite direction, or at least one of them, and that causes them to spin around and choose a new direction, and it ends up being a random walk. But in the presence of a gradient in concentration, they will bias that random walk, and the way they do that is by extending the length of runs for which they detect that the concentration is increasing over that run. So that's a complicated mechanism, but we can do sort of a first pass at asking about the relevance of this result if we consider, say, one of the runs in the trajectory of a bacterium, right? Best case scenario, that run is actually in the gradient direction. So let's sort of focus on that scenario. So one of the legs of this trajectory of my bacterium. So at the beginning of that run, say t equals 0, the bacterium is here. At the end of that run, it's over here. Let's say time equals capital T. And at the beginning of that run, it's exposed to a concentration C1, and it's presumably measuring molecules in its vicinity. And at the end of that run, it's exposed to a new concentration because it's moved up the profile a little bit, C2. And Berg and Purcell essentially argued that the uncertainty, let's say the standard deviation with which either of those, or let's say, sort of the average of those or whatever concentrations is measured, needs to be less than their difference. Okay? And I think that's very reasonable because it says that, if I need to know the difference between the number 10 and the number 9, I hope that the precision with which I measure either the 10 or the 9 is less than plus or minus 1. Otherwise, it's not going to work. So that is to say, sigma c should be less than delta c. And delta c is easy to figure out, right? It's just going to be given by how fast the cell is running times the concentration gradient, because this is just dc dx, times the amount of time that the cell runs, right? The velocity times the time is the distance it moves. The distance times the gradient is the change in the concentration. So this is v t g, right? And for sigma c, I'm going to use this result. Right? So I'll make things a little bit easier on myself by squaring things. So sigma squared over c squared has to be less than v squared t squared g squared. And for this, I'm going to put in 1 over square root of, I also need to divide by c squared. And I'm going to assume that this is on the order of the actual mean concentration C naught. Right? Let's say that the background concentration on which this gradient is on top of it is C naught. So this would be a C naught squared. So for this, I'm going to put in 1 over a C naught dt. That has to be less than v squared t squared g squared over C naught squared. And I'm going to solve for t. Solving for t says that t needs to be greater than, I can pull this t over everything else and then I can raise to the 1/3 power. T must be greater than C naught over a d g squared v squared to the 1/3 power. Okay, so I've turned my statement that the statistics need to be good enough to detect a difference into a statement that it better therefore run for long enough to gather those statistics. The nice thing was that all of these quantities were known from Berg's experiments, right? So I already mentioned that A is about a micron. They were using an attractant for which the diffusion coefficient was about 1,000 microns squared per second. Does anyone know how fast bacteria run? Swim?
Everybody swims 40 lengths a second, right?
Everybody?
Everybody swims, runs 40 lengths a second.
That's basically true, yeah. Bacteria do a little better. It's more like 10 body lengths a second. Yeah. 10 microns a second. They were in a background concentration of a millimolar and subject to a gradient of about 10 nanomolar per micron. Anyway, you can plug in the numbers and you get about half a second, right? This is not a statement of how long their runs last. It's a statement of how long they need to last. in order to gather enough statistics. Does that make sense? Then independently, you can actually look at how long the runs last. And does anybody know how long bacteria usually run before changing direction? Yeah, it's on the order of seconds, right? So the actual runtime, I mean, obviously it depends on conditions, but for his experiments, you could actually look, and it was on the order of seconds. So this is reassuring and perhaps impressive, right? It's reassuring that bacteria do not run for a millisecond before changing directions. Otherwise, we'd be way off for what they're actually doing, right? Yes?
It's a whole distribution of run lengths, right?
It is, yes.
And
It's
how many are less than this cutoff?
well, I think
Is that
to first approximation, it's like an exponential distribution we're talking about. So some. For something shaped like that, the mean is greater than the median, I think. So maybe a lot. But I would say that's a little bit beyond there's too many twiddles here to really discuss that yet. So on the one hand, I think this says that we got the physics right. On the other hand, it says that it makes an implication about how well the receptors and the internal signaling network and everything else biological about the bacterium is working without really having to go into those details. So it says that whatever the bacterium is doing, it's pretty much counting all the molecules that it can and storing that information somehow and doing some approximation of what was assumed, which is that it's averaging or accumulating that data over time. Right, so that was sort of the final conclusion of that paper by Berg and Purcell. Okay, questions about that? So I want to try to sort of build the world of cell sensing a little bit broader than just concentration sensing. Okay, so in a sense, sensing a constant concentration is by far not the most interesting thing that a cell can do. That's already hinted at by the fact that this is not even constant concentration sensing. We kind of cheated a little bit. Gradient sensing is another interesting thing that cells can do. But this type of thinking has a long legacy, and people currently, but certainly over the past 10 or 20 years, have used this type of thinking to consider other types of sensing that cells do. For example, let's say you have two different chemicals in your environment, and you want to distinguish one from the other, right? That's something that has been studied in this field, and people have used this framework. Let's say that you have a concentration and all of a sudden it changes, and you want to know how long do you have to wait before you change your decision in response, right? That's something that Massimo and others have considered. How long do you need to gather statistics before you change your decision? So what I want to do is talk about gradient sensing in a little bit more detail, because this is really just this is a fascinating way in which a cell can detect a gradient, but it's not the only way by far. And there's sort of a much simpler way to do it, but it's really not observed unless the cells are big enough, right? So bacteria are about a micron. Cells in our body are maybe 20 microns big, right? So there's another order of magnitude there that is gained. And what I want to spend a little time doing is asking how these considerations apply to a simpler type of gradient sensing. And the hero of this story, I like that terminology that Gordon used before. The hero of this story will be an amoeba. A fly, yes. This is Gordon's drawing of a fly. Yeah. Yeah. Okay. So amoeba are very good at sensing gradients, but they don't do it like bacteria do it. They have receptors like bacteria do, but they essentially can sit still and detect whether there's more bound receptors on one side of their body than another. And the way that we know that is, well, you know, many detailed experiments, but perhaps one of the most vivid, and many of you have probably seen movies like this, if you, by the way, I've made a sort of perverse choice not to use not to use a projector. I'm going to draw the frames of a movie in my head.
Really fast.
Yeah, I'll just flip the board up and down. So, okay, so, you know, this is a very common and cruel experiment where, you know, you can have a pipette secreting a molecule that an amoeba is attracted to, and you will watch the amoeba sort of migrate toward that pipette, and when it's tantalizingly close, then the experimenter moves the pipette, right? And now it's coming from over here, and the amoeba is like, what happened? And the important thing is that you can see it sit there, and this is about anthropomorphizing. I think I'm doing too much of it already, but you can see it sit there and sort of think about what to do next, and then it starts moving the other way, right? So the point is that assuming that the processing went on here, it was able to change its mind while sitting still, right? And so it has to be doing something static, and we now know that it's essentially comparing receptor occupancies on different parts of its surface. And this can be quantified, this type of motion, in many different ways, but a common way to do it is to define what's called the chemotactic index. Chemotaxis is a fancy word for moving in the direction of a gradient, a chemical gradient. And so if the gradient is this in this direction, so this is sort of the right direction, then the chemotactic index is essentially the angle between the displacement vector describing where the cell actually goes and the direction it should go. And in fact, over many trajectories, the chemotactic index is just the average of the cosine of these angles, so that if it's correct, then the answer is 1. If it's completely incorrect, then the answer is -1. And if it doesn't really know anything, then the answer is 0. And the point is that this has been measured for this type of experiment. In other words, what is the chemotactic index as a function of the distance of the cell to the pipette? And as you might imagine, there's some characteristic fall off. Right? So this was this type of experiment investigating the sort of limits of what an amoeba can and cannot sense was done in a paper I'm thinking of from 2006. Okay, so this sort of sets the stage that there's this sort of very intuitive ability to sense a gradient, and gives you a sense of the data that whatever theory we develop for this would have to sort of speak to, right? Okay, so the question remains, what sets the limit to the precision of gradient sensing in this manner? And then we'll ask whether amoeba actually achieve this limit as bacteria appear to for concentration sensing. Okay, so let's formalize this a little bit. Of course, we're going to start by making the amoeba a sphere. Okay. And let's assume that the gradient direction is in this direction. I'll call that the z direction. And let's actually give it a functional form. So we're going to assume that it's a linear concentration profile. So we'll say C of z is some C naught at the origin where the cell is plus the gradient times z. Okay, and what we're going to be interested in is, as before, the relative error, right, the noise over the mean, but this time for the cell's ability to estimate the gradient, not the concentration. So we're going to ask about the standard deviation in the cell's estimate of the gradient over the mean of the cell's estimate of the gradient. And I think it's instructive to have a conversation again about how we expect this thing to depend on the parameters of the problem. So what are those parameters, and where do they belong, and how does it scale, and do we get the dimensions right, et cetera, just to, you know, get our expectations straight. So I'm going to start by arguing that this should certainly depend on the size of the cell, and that the bigger the cell, the better it will be at sensing the gradient. I don't know how much better, but you know, I'm going to give it some power x. What else? G. Certainly I would expect, well, you tell me, if the gradient gets bigger, this quantity should get bigger or smaller? Smaller. Stronger gradient, maybe easier to detect. So I'll put that in the denominator with a y. Sorry? C naught, okay. So let's imagine same gradient but on top of a different background, right? And so I can ask the same question. If I make C naught bigger, do I expect this quantity to get bigger or smaller? So I hear some loud biggers, some quiet smallers, and when the loud biggers happen, I see some head shakes. So there's clearly, this is not easy. This one's not easy. These have been easy for some reason. This one's, luckily, I can put it anywhere I want, and the exponent might be negative, right? But so just to get the thought process, I think you were the first. So you wanted it to be on the top?
Yes. I mean, because if you're trying to sense the gradient, if the gradient is really, I mean, if the gradient is very small compared to the background, you're not going to be able to sense it.
Okay.
I expect that this quantity will depend on the ratio between G times A divided by C naught.
Which is a similar argument to this. It's a dimensionless version of that verbal argument, right? Yeah. Okay. People, anybody want to volunteer a counter argument? Yeah.
If C naught's like too big, then all your receptors are for like 100%.
Very good. I think that's an argument, even not a counter argument, but that's a good point, right? That's something actually we're completely ignoring for now. Is receptor saturation. So if you think back, we've been ignoring it the whole time, actually. But receptor saturation would also make things worse if C naught got too big, right? I have an argument for why C naught being big might make things more precise, right? And that is sort of a more classic argument that's certainly the case for concentration sensing, which is the more molecules you have in the vicinity, the more you count in a fixed amount of time, and therefore the lower your relative noise. I mean, that's the school I was taught, right? And that's sort of at play, I would argue, for the concentration sensing. So we'd have to sort of, so I don't know, right? I mean, so like I said, I'll go with you guys for now. And okay, I can't use ZW, right? We'll see. Yeah.
It might even be interesting just tangentially to connect it to some comments that Gordon made in the previous lecture, right? That taking derivatives, every time you're taking a derivative, you add, things become much, much worse, right? And here the cell is basically taking a derivative, right?
Yeah.
So it's hard to take noisy derivatives.
Easy to take noisy derivatives.
Yeah. It's hard to take noiseless derivatives of a noisy thing.
Noisy derivatives, yes.
So I completely agree. I don't know if that helps resolve this issue yet, but that's a very good point. Right, the gradient is, especially this mechanism, is sort of comparing the difference between right and left. That's like taking a derivative or a subtraction at the worst. And you're trying to do that with something noisy. What else?
Integration time.
Integration time. I'm going to put that on the bottom. And we had a friend. It had a friend before. D, right? And the reason I call it a friend is because they're the only ones with time, and they need to kind of multiply each other to get because everything else is all about length. So they have to come together, and we'll do something like this. All right. Anything else? There's not really anything more in the problem, I would argue. So I think this is a good starting point. Okay. And of course, what we need, just for dimensional consistency, is we need x plus 3w. This is meters squared, so plus 2u. What's the dimensions of g? One over meters to the fourth. It's derivative of 1 over meters to the to the 3. So we need minus 4y. All that has to be 0 because it's a dimensionless thing. Okay. All right, so how are we actually going to solve this? Last time we had either the perfect absorber or the perfect instrument, the perfect monitor. They got basically the same results for concentration sensing, so I'm just going to choose one. The easier one is the absorber. So I'm going to imagine an absorbing sphere in the presence of a linear profile and ask about its statistics. Okay? And this is following a paper by Robert Endres and Ned Wingreen from 2008. Okay, so to be specific, we have a sphere. It's in the presence of a graded molecular concentration, so there's more molecules over here than over here. This is Z. I'm going to parameterize this in spherical coordinates. I'm going to say this is R, this is theta, and the axial direction is phi. And every molecule that hits the surface of this sphere gets immediately absorbed. Okay? And its radius is A. Okay. The first thing we need to do, I think, is to figure out what the quantity is that the cell could be measuring that would supply its estimate of the gradient. So what I mean is the following. Previously, the task was to estimate the concentration. And we argued that the cell could do that by counting the number of molecules that it absorbs in a time t. If it counts the number of molecules that it absorbs in a time t here, that's not enough, right? Because it wants to know something not just about quantity, but about direction. So what could it do instead?
Count them on one side and the other.
Count how many come on one side and how many come on the other. It has to then choose an axis. So it has to kind of know where the gradient is ahead of time. But otherwise, I think that's a good idea, right? If it just partitioned itself and took a subtraction, that would be a representation of the gradient. At the very least, I would hope that if the gradient doubled, then that measure would double. Yeah. Push, like force. I think that will be very weak. Like, in other words, the sheer presence will be more informative than, well, it will be the first thing to happen. the detection of the molecule, let alone the force. Yeah. Yeah. I don't think we need to consider that.
That's not Chemotaxis, it's like pressure.
Yeah, that would be like, yeah. I want to say Durotaxis, but that's, yeah. Yeah. Yeah.
It like remembers his previous examples.
Ah, so like the bacterium. Is that what you mean? Like comparing something from some time ago to what it is now? Yeah. That would work if it were moving, but we're going to assume that it's stationary. Yeah.
It could do that but rotate rather than actually move in space. If it could distinguish where the receptors were and see, like, as it rotates, which ones change.
Oh, okay. I see. So still maintain some sort of memory of where on the surface things happen, but maybe adding rotation will change the statistics a bit. Yeah. Okay. If I'm going to start with no movement for the cell, but I think you guys are sort of in concert, right? You need to know like where on the surface it's happening. Yeah.
I mean, the receptors are probably not static on the surface of the cell, right?
Not entirely. Yeah.
Could you potentially have like some sort of signaling cascade that causes receptors to move to wherever there's a higher gradient, and then you just have sort of undirected motion wherever there are more receptors?
That's an interesting strategy. I guess I would argue that that's, to first order, not all that different than counting, but it's counting plus focusing your resources in a certain way. Okay, so I'm going to sort of agglomerate the counting at a certain position suggestion, and I'm going to choose a measure that distinguishes part of the surface from another, or I'll propose it, and I'll ask you guys if it's reasonable. So we need some measure of anisotropy is the point. So I'm going to propose a measure which is the sum over all molecules that hit the surface in a time t. I'm going to drop the subscript t, but hopefully you know this is what I mean, of the cosine of the angle at which that molecule hit. Okay. Now, in a way, this is very related to your suggestion because cosine is positive on the right side and negative on the left side. No matter what we propose, what we need to have happen is that the average of the measure we're talking about needs to scale with the gradient. If the gradient doubles, then on average we hope that whatever measure we're using scales proportionally. So let's leave that as a thing to remember, and when we actually compute the average of this, we'll just make sure that it's true. Okay? Yeah?
Sorry, I didn't quite follow that.
Yeah.
You're saying that the cell knows the angle of the
No, we haven't dealt with the other problem. Exactly. So I'm going to assume for now that the cell knows how to orient the theta equals 0 axis. And then we'll do a calculation, and then we'll consider what happens if that's not true. And the calculation we do we'll be able to use to answer the broader question. So hold on to that. Other thoughts before we continue? Okay. So let's actually test whether this is on average proportional to the gradient, right? So in particular, we want to calculate the mean anisotropy. I'll call this the anisotropy. Okay. So there are actually two stochastic quantities hidden in here in a way, right? Because, of course, we don't know for any given molecule what the angle will be. There'll be some distribution over angles at which we expect the molecules to hit. But we also don't know how many will happen in time t, right? So the mean of this is sort of the mean of two stochastic things. But if we assume that every molecule to arrive at the surface of the cell is independent of every other molecule to arrive at the surface of the cell, then every incident of cosine theta is independent from every other one. And so we just have n of them, but n, of course, itself is a stochastic variable. So on average, we have n bar of them. And we can turn this into the product, n bar times the average of cosine theta over whatever angle describes the probability of theta. Or more accurately, the probability of whatever solid angle things are arriving at. But of course, there's axial symmetry in phi. Okay. So to calculate this average, we need to figure out how many molecules arrive in a certain time t, and we need to figure out what's the average of the cosine of the angle of arrival. And we can figure out the answer to both of these questions by, again, considering the diffusion equation with an absorbing boundary. Okay, that's my claim. So, yes. So just to be clear, this is n bar times the integral over a solid angle of the probability of arriving at that solid angle times the cosine of the theta part of that solid angle. And we can get both n bar and that probability distribution from the diffusion equation. N bar would just be the total flux integrated over the time. The probability of the angle would just be the normalized flux, basically. Okay, so let's set that up. So, of course, the diffusion equation reads as follows, and we're interested in steady state. It's not quite as easy as it was before because we have an R dependence and a theta dependence, although the phi dependence should not be there, right, by symmetry. But we can write down the solution. This is, of course, very familiar to many of you from other types of physics problems. Let's make sure we know what the boundary conditions are before we do that. So what are the boundary conditions here? So in math, what I just said was C is going to be some function of R and theta, but not phi. And what are my boundary conditions in terms of R and theta? C is 0 at the surface, right? So C of A and theta is 0. And what else? Yeah. Yes, exactly. So that's a little bit awkward to write, but indeed, it has to have a particular expression far from the cell when the cell is done perturbing the background. So I'm going to write it as follows: C when r is much, much greater than a is the cosine theta expression that we have here, right? It's C naught plus g, and in spherical coordinates, my z is just r cosine theta. Okay. So those are my two boundary conditions. Okay. Apart from that, I mean, this will sort of set the uniqueness of the problem, but apart from that, the problem is very general and straightforward, right? The general solution to the steady-state diffusion equation, or the heat equation, or the Laplace equation, it can be expanded in many different bases, but in spherical coordinates, I'm sure you're all familiar with YLMs for the angular part and a particular function for the radial part. So in general, we can write this as the sum over L and M of some capital R sub L in radius and YLMs in theta and phi. But of course, because we know there's no phi dependence by symmetry, we just have m equals to 0, which collapses this sum, for which YL zeros are just the Legendre polynomials as a function of cosine of theta. And just to remind you, P0, so Legendre polynomials as a function of their argument, P0 is 1, P1 is the argument, P2 is not going to matter. I think there's a half there, there's an x squared, 3x squared minus 1, and so on. Okay. And the radial part is sort of the generalization of the radial dependence that we saw before. It is some coefficient times r to the L plus some other coefficient times r to the minus L plus 1. And if there were no theta dependence, like we saw in the concentration sensing case, then L would be 0. This would be my constant, and this would be my 1 over r term. Good. So that is to say, obeying the symmetry, we get the sum over L of AL r to the L plus BL r to the minus L plus 1 times PL of cos theta. Okay.
We have also some coefficient CL, which measure how important is each component.
So I think I'm okay there, because if I wanted to, I could factor out an A, and then this one would be, BL over A or something. I could make either of these the global coefficient. Yeah. Okay. Let's now specialize with the boundary conditions, right? Which one would you like to apply first, 1 or 2? So I have a problem with applying 2 first per se, because there's no a, little a, in my expression yet. So I don't know how to enforce the r much greater than a. So let's apply 1. So if I apply 1, it says that C of A and theta is 0, and I have a sum that must be 0. What do I do with that fact? Yeah. Yes, exactly. Legendre polynomials are linearly independent. That means every one of these bracketed things is actually forced to be 0, and that sets, for example, B in terms of A, big B in terms of big A. And that actually gives me, that modifies my solution to put a little a into the problem, right? So now C of R and theta is the sum L equals 0 to infinity of AL R to the L. I'm going to factor out an R to the L times 1 minus the quantity A over R to the 2L plus 1 times my Legendre polynomial. Okay. So now it's very clear that to apply the second boundary condition, I can simply neglect this term, because 2L plus 1 is always positive. If I neglect that term, then I have a function that needs to agree with my boundary function far from the cell. And if I explicitly write that out, then the 0th term looks like A0 times R to the 0 times P0, which is 1, plus A1 times R to the 1 times P1, which is the argument itself, which is the cosine theta. And there's more, but I hope you'll agree that the subsequent coefficients need to be 0. Once again, because the Legendre polynomials are independent, so we need to match this thing term by term. Constant, cos theta, and everything else is 0, right? So this says immediately what these things are. A0 is C0, and A1 is G. And so my full expression then I hope it was okay that I went through this. I just wanted to make you guys feel like you're in an E&M class again. That's true. Yeah, that's right. Right. So the final expression is C R and theta is C naught times 1 minus A over R. That's the first term. Plus GR times 1 minus A over R cubed from the second term times cos theta. Okay. I feel pretty good about this because if the gradient goes to 0, then we got exactly what we did for the absorbing for the concentration in the absorbing sphere case, which is the uniform concentration. Good. So as before, this is not the most important thing. The most important thing is the flux, and in particular we want to know what the flux is as a function of theta on the surface. So we want sort of the flux per area, right? And that's nothing more than, so I'll call it J of theta, and that's nothing more than d times dc dr evaluated at the surface. It's positive because we want the inward flux again. And so I take a derivative with respect to r. I get a 3, no, let's see. Okay. I take a derivative with respect to r, and I get an r squared on the bottom here, but I plug in a, I get an a on the bottom. I get a c naught on the top, and I get a d on the top. So this first term gives me d c naught over a. Second term, I get a, I get a d, and I get a g cosine theta from here. I can put this r in. I get a minus r squared on the bottom. I take a derivative. I get a plus r cubed. That kills the a cubed. I lost it. That was a minus r squared. Pulls down the 2, so I have a 2. Then it's an r cubed. That kills the a cubed. So it's a 2. Ah, and this became positive, and it's a 1. Okay. So this is times 1 plus 2, which is a 3. Okay. So that's the angular dependent flux, right? From that, we can get the two things that we wanted. We can get the total number of molecules coming in by just saying n bar is T times the integral over all solid angle of this flux. That's not enough, right? We need to integrate not over just all over angle, but also the area. But it's on the surface of a shell of area A, so I can put the a squared here. If this were independent of theta, my integral over the solid angle would give me my 4 pi, and this would be like multiplying the flux by 4 pi a squared by t. Yeah. So if you do that, you find that the cosine integrates to 0. This does not. And what you get is 4 pi a c naught dt. Okay. You will not be shocked to hear that this is the same answer that we got when there was no gradient present, and it just says that tilting the concentration doesn't change the total number of molecules that arrive. Okay. The second thing we can get is this probability of the solid angle, right? The probability of the solid angle is j over the integral of j. Dummy index. And for that, we do retain an angular dependence, obviously. It's here. This is just a normalization factor. And we get 1 over 4 pi times 1 plus 3g a over c naught cos theta. Okay. Oh, by the way, oh, no, we're not there yet. Sorry. All right, so we plug that in. We can now complete this integral at long last. And what we get, is that alpha bar is 4 pi a squared times g dt. Now this is very comforting because indeed the mean of our measure that we chose to be the cell's statistic is proportional to g, right? So if g doubles, indeed what we're saying that the cell should measure also doubles. This doesn't depend on all the players in our problem, does it? There's something missing. What is that? C naught. Why doesn't it depend on C naught?
We're measuring the gradient.
We're measuring the gradient. We've chosen a measure that basically takes the cosine of the angle, which is the best we could do to basically do right minus left. And if you do right minus left on a linear function, you get rid of the background, right? So we're not only measuring something proportional to the gradient, we're measuring something that has like subtracted away the background, right? Okay, good. All right, we're only part of the way there because in addition to the mean of what we're measuring, we need to know what its variance is. That will help us answer finally the question of what is the precision. The implication being, now that we know that alpha is proportional to g, then we can basically say that this thing that we want, the relative error in g, is equal to the relative error in alpha. So we have alpha bar, now we need the variance. Okay. So by definition, I mean it's easy enough to write down, the variance is just the average of alpha squared minus alpha bar squared, and we just did alpha bar. So really this amounts to what is the average of alpha squared. And since I have a definition of alpha, I can just plug this in. This is the average of the sum over I times the sum over j of cos theta I cos theta j. And I'm going to make my life a little bit easier by separating this into the j that is I and the j's that are not i's, right? So are not I. So that is to say this is the sum over I and all the j's that are not I of cos theta I cos theta j plus the part where j is I in which case you get a cos squared. Now the reason I did this, because this is now guaranteed that particle I and particle j are different. Yes?
Wait, should both sums go up to the same n? Or is the idea that n is also stochastic variable?
Yes, that is a true statement. Yeah, yeah.
So n is presumably large.
Yeah.
And so the fluctuations in n will scale as about square root n. And if you really do the analysis, you will see that it's going to be a second order collection somewhere. It's quite interested here.
Yeah. I mean, we're going to go with that probably, but I mean the real thing is that you want to call this an n prime, and then you want to know whether it's enough to know that the mean of n and n prime is the same or something like this. Hold that thought maybe, and we'll see which of the next steps I write down is most offensive. So, okay. Knowing that I and j are truly different particles, these are statistically independent, and therefore this is just two factors of the average of cosine theta, the very same thing we were dealing with before, but now squared. And how many of these terms are there? Well, if these were both n, and we took away one, then this would be n times n minus 1. And we would need the average of that because it's a stochastic thing. Now this is the most offensive part, I think. Let's see. If I keep a prime there, I don't know. I might get confused. So continue to keep that in mind. This term is fairly straightforward. It's just n copies of the average of cosine squared, which we have not computed yet. So that would be n bar times average of cosine squared. Okay. If we are okay with this expression, we can invoke the fact that n is a Poisson variable, which is to say that this expression is average of n squared minus n bar, but n squared is nothing more than sigma n squared plus n bar squared minus n bar. And of course, for a Poisson variable, the variance equals the mean. So this whole thing is just n bar squared. So maybe as you're falling asleep tonight, you can think about whether this is exact or not. Okay. And what's nice actually is that n bar cos theta, n bar times average of cos theta, is actually just alpha bar. So this and this are going to kill this when we plug it back into the variance. So essentially, this just says that the variance is n bar, which we already calculated, times the average of cos squared theta, which we have not calculated, but it's easy enough to do. Average of cos squared theta is simply the integral over the solid angle of p of the solid angle, which we got from the flux, times cos squared of theta. And that's just an integral. You can do it. You get a third. Okay? So this is actually just n bar over 3. And before I stop, I'm going to address Liam's question. How did we know that the cell knew the right direction in the first place? We did not. Instead, we could have picked an arbitrary direction, decomposed it into x, y, and z. And this would be the variance for the z component. But it would also be the variance for the x and y components, because the noise is the same, even if the mean is different along each direction. So because of the lack of knowledge a priori of the cell in the gradient direction, this really should be n bar. Okay. All right. Next time, we will put all this together, see whether we were right or wrong about our sort of dimensionality assumptions, or whether things are on the top and on the bottom. We will compare this result to data from Amoeba, and we'll start to talk about more interesting things when cells actually work together. That's it. Question? Ilya?
Yes. So here you're choosing alpha, right? You decided that I'm going to look at cosine. Right?
Yeah.
That's a choice.
Yeah.
So here the cell is supposed to know what a cosine is, right? In some sense. So can we reformulate this problem in a way that we do not have to make arbitrary choices, right?
Yeah.
So try to do some kind of maximum likelihood inference of a gradient
Well,
or something
yeah.
like that, right?
So that way of thinking is exactly what they did in this paper. They used maximum likelihood to ask what is the measure which would be most informative about the gradient, and that is the answer, the cosine. So while I picked it arbitrarily, it doesn't have to be that way. Although I guess I would argue that any measure which on average is proportional to the gradient would work, although the result of the maximum likelihood might argue that there is only one, and it's the cosine. Does that make sense? Yeah?
I have another question. So I guess we could also imagine that the cell measures like gradient in the flux along the surface. So if you have like different theta values, then you would expect that like at the edge towards the gradient, you have basically zero gradient because it's kind of circular. Whereas on the top, you have like a maximum gradient. And so I was wondering if cells can actually measure.
Oh, wow. Okay, I see. So you're saying like particles impinge this part of the surface normally. No, that's not quite right. What I'm trying to rephrase. But like, yeah, you're saying that two very close sites would have the same flux here, but two very close sites would have different flux here. That's like a very local measurement that doesn't take advantage of the sum total of all measurements around the surface of the cell. So I have a feeling that would be much worse. And instead, I think that the computation that amoeba, for example, do is closer to this, in the sense that they have diffusible internal messengers that ostensibly compare concentrations across the length scales comparable to the cell itself. Yeah. We'll talk about like local gradient and global gradient kind of competitions when we start talking about multicellular stuff. Other questions?